Um, One question that often pops up when discussing image processing concepts is the size of the mask. Understanding its importance is crucial as it plays a significant role in image manipulation. The bigger the mask, the more neighbors contribute to the filtering process. This results in a smaller noise variance at the output, a wider spread of noise, and more blurring. However, it's important to note that a larger mask also means a more computationally expensive process. Now, onto the Gaussian filter. This is a special type of averaging where the coefficients form a two-dimensional Gaussian. This method gives more weight to the central pixel and less to the neighbors. The farther away the neighbors, the smaller the weight they hold in the process. But how big should the mask be in a Gaussian filter? The standard deviation of the Gaussian, represented by S, determines the amount of smoothing. To adequately represent a Gaussian, the samples should cover 98.76% of the area. For this, we need a mask size M equal to 5 times the standard deviation. After understanding the Gaussian filter, we move to a different kind of filtering at nonlinear filtering. Here, we replace each pixel with the median value of all the pixels in the neighborhood. This approach has several unique properties. Nonlinear filtering is, as the name suggests, nonlinear. It doesn't spread the noise, unlike the previous methods we discussed. This filter can effectively remove spike noise, making it quite useful in specific scenarios. However, it's important to remember that it's also more expensive to run. In summary, the mask size is a crucial factor in image processing, affecting the output quality and the computational cost. The Gaussian filter uses a particular case of averaging, with more weight on the central pixel and less on the neighbors, with the mask size dependent on the standard deviation of the Gaussian. Lastly, nonlinear filtering employs a different technique, replacing each pixel with the median value of the neighboring pixels, effectively removing spike noise but at a higher computational cost. Understanding these concepts forms a solid foundation for further exploration into the world of image processing and manipulation.